In the first session only, I told you about information and entropy. Let's get some more insight into what is or what are the properties of information and uh, entropy. Now, we can say we have a source that generates discrete information. Let's say S0, S1, S2, and up to, if this starts with 0, we can say this is up to n minus 1 or k minus 1. Let's use k here. Okay. And the probabilities associated with this can be written as P0, P1 up to Pk minus 1. Okay. This is the probability associated with this. Now we know that if we take P, let's say I, from where I equal to, we have started from 0 up to k minus 1. If we have summation of this will be given as, this will be equal to 1. This is we know. I told you uncertainty, then was surprise, information, these were the terms used. Uncertainty. What happens? You are, before any event occurs, you have uncertainty. You don't know what the result is. After the event occurs, you are surprised. Like, if you have a coin, you don't know what will be the result, a head or a tail when you toss it. So you are uncertain. Then what happens? You toss the coin. That is, the event occurs. You are surprised. Oh, I got head. This is surprise. And then what happens? You get information. That is, the outcome is a head or a tail. That is, the whole process is resolution of what? Uncertainty. Resolution of uncertainty. Okay. There's nothing new what I am saying. These things I have said in my first class only. What I want you is to understand them better, because we will slowly be moving towards mathematical modeling of information and mathematical modeling of entropy. We'll treat it as stochastic process. That is, process with random variables. So you should understand these in mathematical modeling terms also. Now I told you that day only that, let's say, we represent it like this: information for some message. This is a message that is coming out of the source, kth message. This is equal to log of 1 by the probability associated with this message. And if we are talking of binary digits, we will use log 2. This is, we have done. So let's see what are the properties of information. First property that you get from here is that ISK is 0 for Pk equal to 1. That is, if the probability of the event is 1, the information content is 0. This we had discussed that day. This is mathematical representation. Second, we know that this Pk actually lies between 0 and 1. And since it lies between 0 and 1, you have this value which tells you that this Is will be greater than 0. It will be 0 only for Pk equal to 1. Otherwise, it will be greater than 0. This is the second property of information. Third property is, if you have two information, let's say K and the second one is M. Okay. If Pk is greater than Pm, if this probability is greater than this, then this is less than this. The information content is less. These things you know intuitively. What you need to know is the mathematical modeling. Okay. So these are the properties of information. From here, we had defined entropy. What was entropy? It was the expectation of I, that is information. Let's say we are using S, so HS. This was nothing. This was defined as expectation of this thing, which is actually your Pk into log of pk. And if you are using binary system, this is a log base of 2, where k start from 0 to k minus 1. Clear? This is what we had done that day. We had found this. So based on this, we have certain properties of entropy. Entropy is what? Entropy is average information per message or per symbol. So what are the properties of entropy? Let's see. So let's say our ISK, we had defined it as log pk minus log pk. Now if for binary digit this is 2, if p is half, that is you have 2 digits only, bits in binary system, if it is half, or if we have k number of information, if this is equal to 1 by k, like here what we get, this becomes 1, that is 1 bit of information. From here we have a very important property for entropy, that entropy lies between log k, base 2 for binary. This is a very important property. HS becomes, the entropy becomes 0 when pk is equal to 0, sorry 1. That is when probability of messages or the message is 1 if we have k number of messages. One message has probability 1 and others have 0. Obviously others will have 0 because when you will add all probabilities it has to be 1. So in that case your entropy, that is average information, will be 0. And second is when your probability is equal to actually 1 by k. K is the number of messages. For binary there are 2 messages, in decimal you have 10 messages. So when pk is equal to 1, that is all the messages are equiprobable. This means all messages are equiprobable. We have seen this. Then your HS becomes this, that is log of k, base 2. So if for binary we are talking, this is 2, we'll have HS equal to 1. Clear? So these are the two properties of entropy. You should understand. Now from here let's see the entropy of a Bernoulli random variable. What is Bernoulli random variable? That is either you have 0 or you have 1. Let's say the probability associated with 0 is P0 and with 1 is P1. Obviously we know P1 will be equal to 1 minus P0. You have 2 messages only. So what happens if you look at it? We'll have HS equal to, that is summation of this. So this will be equal to minus P0 log P0 minus P1 log P1. Okay, but P0 is equal to, sorry, P1 is equal to 1 minus P0. So this becomes 1 minus P0 log P0 minus 1 minus P0 log 1 minus P0. Now this is a very important function in digital communication when we are using binary system. So it has been given a peculiar name, that is called entropy function. Okay, so entropy function is basically this thing. What is the property of this entropy function? So the property is either P0 is equal to 0 or P0 is equal to 1. In both these cases your HPO, that is your entropy, becomes 0. These are the first two properties, that is either this has probability equal to 1 or this has probability equal to 1 or this has probability equal to 0. What you will get is you will have 0 entropy. Next thing is that when your probability P0 is equal to probability of P1, that is 1 by 2, your entropy will be 1, which is maximum, HS max, that is equal to 1. So this is the property of this entropy function. Clear? This is what we mean when we say entropy of a Bernoulli random variable. Let's plot this function, this entropy function. So if you plot this entropy function, here we are taking HP0 this side and here we are taking P0. what you'll get is the function will be like this, and the maximum will be, this is not even, you can draw even diagram, this will be at half, that is p0 equal to half, this will be equal to 1. This is your entropy function. This is a diagram for entropy function. Okay. Now let's see the entropy of an extended source. What is the meaning of extended source? Let's say our source is what we have been saying, S0, S1, S2 up to Sk minus 1, and the entropy of this source is Hs, that you know what is the value of Hs, that is the expectation of Isk. What is an extended source? Extended source means, let's say this has two symbols, this source has two symbols. Extended source means, let's say extended source, this means S0, 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 S1. So we have two different possibilities here. Okay. Not only two, it has four. How? S0, we have associated S0 and S1 with S0, and then with S1, S1, S0, S1, S1. So this is the meaning of extended source. That is, from the source we have extended it. We have created another sequence of symbols. Basically what we do, we have k number of symbols in S. What we do, we take n number of symbols in one block. We consider it as one block. That is, we have S0, S1, S2, S0. Let's say this is n number of sequences for as one block. Then again S1, S0, S2, and so on as another block. So we have n number of symbols in one block, and we have k number of such blocks. So effectively what you get is, if you take the probabilities, they are actually multiplication of, for example, if probability is p1 and we get n p1 number of symbols repeating there. So probability is this, and then you multiply with the second probability. We have done this in our earlier videos. What I want to emphasize now, that the probability of the extended source, so let's say we write it like this, Hsn to the power n, raised to the power n, is actually equal to n times Hs. You should keep this formula in mind. I'll give you an example so that you understand it. Let's see an example. We have three symbols, S0, S1, S2, and the probabilities associated with these symbols are 1 by 4, 1 by 4 and 1 by 2. What is the entropy? You know, it is pk log 1 by pk base 2, k equal to 0 to k minus 1. So this is 0, 1, 2. We'll add all of them. So what is this? This is 1 by 4 log 1 by 4 base 2 plus 1 by 4 log 1 by 4 base 2 plus 1 by 2 log 1 by 2 base 2. So if you take the log base 2 of this, what you will get is 3 by 2 bits. The unit will be bits for binary digits. Okay. So if we have these three symbols with these three, or the probability associated with these symbols are these, then the entropy is this. This is how we calculate the entropy. Now let's say we extend this source. What is the meaning of extend this source? Extending the source means, if there were k number of symbols in the original discrete source, then in the extended source you will have k to the power n number of symbols. So here we had three symbols. Okay, you can see 1, 2, 3. So this will be the second order extension will be 3 square, that is, we will have 9. number of symbols. What will these symbols be? S0, you will associate these three terms with S0, 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 S1, S0, S2. So with first, then S1, S0, S1, 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 S2. Okay, I'm clubbing them so that you don't get confused. And then finally S2, S0, S2, S1 and S2, S2. What will be the probabilities associated with these symbols, these extended symbols of second order? S0, S0, so 1 by 4 into 1 by 4, that is 1 by 16. S0, S1, 1 by 4, 1 by 4, 1 by 16. S0, S2, 1 by 4 into 1 by 2, 1 by 8. S1 into S0, see S1 into S0, 1 by 16. S1 into S1, this into this, that is 1 by 16. S1 into S2, 1 by 8. S2 into S0, this into this, so 1 by 8. S2 into S1, this into this, 1 by 8. S2 into S2, 1 by 4. So these are the probabilities associated with these symbols. What will be, this is second order, so I am writing S to the power 2. We have seen, we have just deducted that this has to be equal to this thing. So according to this formula or this expression, we know this will be equal to 2 into HS, that is 2 into 3 by 2, we got 3 by 2. So this should be equal to 3 bits. See, what you will do, you will take 1 by 16 log 1 by 16 plus then again 1 by 16 log 1 by 16. So this is for 1, 2, 3, 4, 4 times. So I am putting 4. Then 8, 1, 2, 3, 4, 4 times 1 by 8 log 1 by 8 base 2. Okay, 1, 1, 1, 1, and then finally this 1 by 4 log 1 by 4 base 2. You take logarithm, you will see this comes to 3 bits. Okay, so from this formula also if you apply, you can get 2 into 3 by 2, that is 3 bits. This is the meaning of extended source and entropy of extended source. You should understand this. Okay. Now we'll see one of the most important topics, that is called Shannon's first theorem, that is the source encoding theorem. It's called source encoding theorem since it was given by Shannon. It's called Shannon's first theorem. What it is, let's understand. We have dealt with source encoding. What is source encoding? Let's say this is a discrete source. This is a discrete source. We are talking of discrete sources only. We are not talking of continuous source. You understand the difference? Continuous source, this would be the signal, and this discrete source, you will have symbols S0, S1, S2 coming out at certain intervals of time. So let's say this is a discrete source. What we are getting is SK symbols out of this source. Then we put a system, a circuitry, or better to say an algorithm. We put an algorithm that actually converts this source into a source that is actually used in transmission. The process of representation of symbols. We represent symbols. So the process of representation of symbols is called source encoding. So this is basically called source encoder. So what is happening? This is a discrete source. It is generating data. So the process of representing data generated by a discrete source, that is called source encoding, and the algorithm that actually converts this generated data into a code is called source encoder. For binary, let's say this SK has been encoded to binary code word. Clear? SK is converted to BK. This is an algorithm by which we convert the data generated by the discrete source into a code word suitable for transmission and use in digital communication systems. So this algorithm requires particular type of hardware. So you'll have source encoders also, hardware source encoders which follow particular algorithm. We'll understand algorithms. What are algorithms for source encoding. First of all, let's understand that if we have sk, and if the sk, the symbol sk, the kth symbol has code word length of lk. Let's say the length of this symbol, when you represent it in binary form, it has a code length of lk. Then from here what we can do, that the average code word length, that can be represented as probability associated with the symbol into the code word of that symbol, from k equal to 0 to k minus 1. So this is the average code word length of the symbol generated by discrete source. Okay, this is average code word length. Average code word length. So this is average code word length, which is, you can say, average number of bits per symbol. In case of binary system, this average code word length is actually average number of bits per symbol. So if you take 3 bits to represent a symbol, if the average number of bits taken is 3, that is the average code word length. Okay. So now from here, what I am saying average number of bits or average number of code word length. Then definitely there will be a minimum number of length. In that, when this is average, this means some code lengths are higher, some code lengths are lower than that value. So if we say L min is the minimum number of code word length that has been used in this particular system, then we define efficiency, code word efficiency, which is L min by the average number of bits used for per symbol. Okay, so this is code word efficiency, code word length efficiency. Obviously, this is minimum value. What we know is this is greater than L min. Therefore, what we'll have? We'll have eta less than 1. Efficiency is always less than 1. Okay, clear up to this? And what can be at the max? At the max, this L min can be equal to L. So in that case, L will be equal to L min. So either L is greater than or equal to L min. From here we get eta is equal to or less than 1. Now here we have Shannon's first theorem, that is the source encoding theorem. It states, Shannon's first encoding theorem states that this average code word length is greater than or equal to the entropy of the source. This is Shannon's first theorem. The average code word length, what is this code word length? You know, source, we have converted it to binary form. Then that average bits per symbol, so this is L, that has to be greater than or equal to HS. This is Shannon's first theorem. From here you can find the value of eta. Eta is now what? It is HS by L. Okay, clear? This is Shannon's first theorem. So you will get, if you are asked what can be the minimum code word length as per Shannon's first theorem, you will have to find the entropy. We found entropy for certain symbols with certain probabilities. You will have to find it, and then you will state that the average code word length has to be greater than this. Okay.